Welcome back to Dr. Liu's VCE Physics. Today's topic is light as a particle, as presented in the 2024 VCE Physics exam. Let's learn together. If teachers, parents, or students notice mistakes in my explanations, please provide me with your feedback. Diagram P depicts 5 discrete energy levels within an atom, alongside 5 specified electron transitions. These transitions comprise 3 high-energy de-excitations, from E5, E4, and E3 to the ground state E1, and 2 lower-energy de-excitations, from E5 to E2, and E5 to E3. Diagram Q provides 4 possible emission spectra. Among these, spectrum D features 3 high-frequency lines at the rightward end and 2 lower-frequency lines at the leftward end. An electron gun is a key component of a transmission electron microscope. This microscope leverages the wave properties of electrons to examine specimens too small for optical microscopes. As shown in Figure 19, a beam of electrons starts from rest at plate A in the electron gun and accelerates through the potential difference, V, between plate A and plate B, exiting plate B with a speed, V. Given the de Broglie wavelength of the electrons, their momentum can be calculated using the de Broglie equation. Note: Planck's constant is measured in joule-seconds. When the electron beam passes through a crystal, Sally argues that no detectable diffraction pattern will form because the wavelength is less than the intratomic spacing. Max disagrees, claiming a useful diffraction pattern will be obtained. Max is correct. A useful diffraction pattern will be produced because the de Broglie wavelength of the electrons and the intratomic spacing are of the same order of magnitude. In this experiment, Sally and Max adjust an electron gun to produce electrons with an energy of 600 eV and a de Broglie wavelength of 0.0501 nanometers. They then direct this electron beam through a thin foil, observing a diffraction pattern. For comparison, they also pass X-rays through the same foil and find that both the electron and X-ray diffraction patterns have the same dimensions. The wavelength of the electrons or photons dictates the spread of a diffraction pattern. Since both patterns exhibit identical spacing, the electrons and X-rays must have the same wavelength. The identical diffraction patterns produced by X-rays and electrons indicate they share the same wavelength. As X-rays are a form of light, their speed is the speed of light. To calculate the X-ray's energy, we can combine Planck's equation and the relationship between frequency and speed. A critical point to remember is to use Planck's constant in electron volt second, eV times s, as using the joule seconds, J times s, value is a frequent source of error, since the energy is asked for in eV. In an experiment on the photoelectric effect, Nicola uses a photocell and different frequency filters for electromagnetic radiation. For each chosen frequency, she systematically increases the voltage until the current stops, recording this stopping voltage. Throughout this process, the frequency, or wavelength, acts as the independent variable, the recorded voltage is the dependent variable, and factors such as the light source, its intensity, and the type of metal plate are kept constant as controlled variables. The paragraph describes how to plot experimental data from a table where frequency is the independent variable and voltage is the dependent variable, with a voltage uncertainty of plus or minus 0.1 V. It instructs to plot the data with uncertainty bars and then draw a straight line of best fit. The text highlights a common error, incorrectly drawing the line of best fit by only connecting the first and last points, which would visibly misrepresent the trend of the middle data points. The gradient of your frequency versus voltage graph is equal to Planck's constant, and its unit is electron volt seconds, EV times S. This question is designed to see if you can apply methods of analyzing data, as detailed on page 59 of the study design. It's crucial to show how you calculate Planck's constant from the graph's gradient, not just give the final number. Demonstrating this calculation is essential for receiving full marks. This graph provides a straightforward way to identify two key properties of the metal: its work function and threshold frequency. The work function, which is the minimum energy required to liberate an electron from the metal surface, can be read directly from the y-intercept of your graph. Correspondingly, the threshold frequency, the lowest frequency of incident light capable of causing electron emission, is given by the x-intercept. Understanding the stopping voltage and photoelectrons. In a photoelectric effect experiment, the recorded voltage measurements, specifically, what's often called the stopping voltage, give us crucial information about the maximum kinetic energy of the emitted photoelectrons. This can be a tricky concept for students, and it's easy to get confused. A common mistake is to mix this up with the energy of the incoming photons, or simply to say the energy without specifying that it's the maximum kinetic energy. The reason this distinction is so important is that not all photoelectrons leave the metal with the same energy. The stopping voltage specifically measures the energy of the most energetic ones. The widespread difficulty with this question suggests that many students don't fully grasp the fundamental principles of how the photoelectric effect works, and what the measured voltage truly represents. Using a different metal for the photocell would cause Nicola's graph to shift vertically, either up or down. The gradient of the graph, however, would be unaffected. This vertical displacement would be due to a change in the metal's work function, altering the y-intercept, and consequently, its threshold frequency, shifting the x-intercept. The gradient, which represents Planck's constant, would remain constant. Blue light carries higher energy than green light because blue light has a higher frequency. In a photoelectric effect experiment, point P represents the stopping voltage. Therefore, if the green filter is replaced with a blue filter, the stopping voltage, point P, will shift to the left on the graph. This is because the higher energy of the blue light will cause photoelectrons to be emitted with greater maximum kinetic energy, requiring a larger opposing voltage, a more negative stopping voltage, to bring the current to zero. If blue light replaces green light while the power level remains constant, the energy of each individual photon increases, because blue light has a higher frequency. To maintain the same total power, the number of photons emitted per second must decrease. This reduction in the number of incident photons will lead to fewer photoelectrons being ejected, consequently reducing the photocurrent. Therefore, the horizontal line Nm, which represents the photocurrent, will be lower. A common mistake is to assume the photocurrent stays the same, which incorrectly ignores the crucial information about the constant power of the light source. The photoelectric effect strongly supports light's particle nature, photons. The wave model fails to explain three key observations: the threshold frequency, the instantaneous emission, no time delay, and how frequency directly affects photoelectron energy. In contrast, the particle model successfully predicts all these experimental results. Students must compare these model predictions with experimental findings to conclude that only the particle model accounts for the photoelectric effect. The light as a particle section accounts for 29 out of 120 total assessment marks, representing 24.2% of the overall assessment. This section includes one multiple-choice question, worth 1 mark, and 2 short answer questions, worth 28 marks. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.